Welcome back. We've covered attention, but there's one big problem we haven't solved yet. The transformer has no idea what order words come in. That's what episode 5 is about, positional encoding. Here's why this matters. Self-attention looks at all tokens at the same time. It has no built-in sense of sequence. So dog bites man and man bites dog would look completely identical to the model. Same tokens, same embeddings, but completely different meanings. That's a serious problem. The fix is straightforward. We add a unique positional signal to each token's embedding. So dog doesn't just carry its meaning vector, it also knows it's at position 1. Bites knows it's at position 2. Man knows it's at position 3. Now, the model has both meaning and order. But how do we encode that position signal? The original transformer paper used sine and cosine waves at different frequencies. Each dimension of the position vector gets a different wave frequency. So every single position across the entire sequence ends up with a completely unique combination of values. And the implementation is elegant. The position encoding vector is simply added to the token embedding vector. No extra weights, no learnable parameters. Just a fixed mathematical signal layered on top. The result is the final input that actually goes into the transformer. Without positional encoding, word order is completely invisible to the model. With it, every token knows exactly where it stands in the sequence. Simple idea, massive impact. We've now covered every individual piece: embeddings, positional encoding, self-attention, multi-head attention. Time to zoom out and see how they all fit together inside the transformer architecture. At the highest level, the original transformer has two halves: the encoder, which reads and understands the input, and the decoder, which generates the output. The encoder passes its understanding to the decoder as something called a context vector. Inside the encoder, here's what happens step by step. First, input tokens go through embedding plus positional encoding. Then, through multi-head self-attention, where every word looks at every other word. Then a feed-forward network processes each token. This entire block repeats n times, usually 6 to 12 layers stacked on top of each other. The decoder is similar but has one extra step. It starts with the tokens generated so far, adds positional encoding, then runs masked self-attention. Masked because it can only look at past tokens, not future ones. Then it runs cross-attention, where it reads the encoder's context. Then a feed-forward network, and finally predicts the next token. Put it all together and the full pipeline looks like this. Input text goes into the encoder. The encoder produces a rich context representation that flows into the decoder. The decoder generates output one token at a time, passing each new token back in as input for the next step, through a final linear and softmax layer to pick the most likely next word. And there it is, the complete transformer. Every single concept we've covered in this series lives inside this architecture. This is the foundation that powers GPT, BERT, Claude, and virtually every modern LLM. See you in the next episode.